Our final talk for the EasyBuild user meeting is creating an open HPC ecosystem with RISC-V. Over to John.
Thank you very much. Good evening or good afternoon, good day, everyone, depending on where you are. I'm excited to be here. Thank you for the invitation. Today, we're doing something a little bit different, talking about RISC-V and an open ecosystem that we can create with that. And with that, I wanted to start off with providing an outline and overview. So we'll talk about some technology trends that are getting us there. I want to define, or at least give you an insight for what RISC-V is. We'll go into some of the work I've been doing with a special interest group and how to get started and actually getting started. So all this stuff will come together because I want to leave you with some tools and capabilities beyond that. And as you know, fundamentally, technology has been changing quite a bit. And today within the HPC stack, we're seeing a couple of different things. At the top, we have a bunch of applications that are basically open source to some level. And you'll have examples of those, whether they're GROMACS or OpenMP, a bunch of different workflow schedulers, all the way down to Linux, which we can deploy on our own or pay someone to support and push that out. We've seen some movement on the hardware side. What I have here is OCP. This is the Open Compute Platform. These are folks generally on the hyperscale side that have pushed out designs for integrating hardware. So these are boxes, servers, that kinds of things. And it's usually a partial implementation. What I mean by that is you might get a server design and be able to build that, but you don't have the BIOS or the firmware to make that actually functional. So that's part of the challenge. But what we've seen so far is basically this de facto standard for OS being Linux, and the software landscape being taken over by open source, which is great. So we get common platform specifications, interfaces, which we can use. And this really then allows us to accelerate what we can build on top of. And that's the exciting part of what open source provides. And obviously we can crowdsource all of these things. So this gives us a large body of individuals to help for a variety of different problems. But what we see so far is that the CPUs, GPUs, ASICs, hardware, all those stuff tends to be closed. And so when I think about doing design in this area, and especially coming from a research perspective, working at Barcelona Supercomputing Center, it's very difficult for us to penetrate those closed ecosystems. And so, this is what we want to change moving forward. Now, that's just one part of this is, okay, well, I'd like to be able to modify my CPU or my accelerator. That's great. That's research. But fundamentally, we're also seeing technology trends get us there as well. And so really what that means is we're seeing on the software side massive penetrations of open source software, everything from IoT all the way to HPC and different components with that. On the actual fabrication side, it's a combination of slowing down Moore's law, and depending on who you talk to, that's either stopping or slowing down. And this is really how many transistors I can pack in a physical area. And that's where we were getting performance. There were other things that were giving us performance before that. But that's also kind of exacerbated by the reduction in power constraints within that. So the inability to put more transistors on a die plus power constraints are really leading us to specialization. So we're creating special purpose functional units, accelerators, domain-specific accelerators to be more cost-effective, to have higher performance, and obviously use less power. And so this is part of that aspect where what I've talked about before is you saw software, right? I can play with the software, I can do a bunch of things there, but in a closed ecosystem with hardware, doing the software hardware co-design to get to the specialization piece is very difficult. And so it's required. How do we do that? And that's part of the questions that we're answering today. And so now there's this fundamental evolution of what's available. And there have been open source ISAs before, instruction set architectures, but today there's been a change. It's taken probably about a decade with RISC-V. So RISC-V is a ISA that's coming from University California, Berkeley. It's been pushed out into the open domain. More recently, Open Power has been pushed out there as well by IBM. And there are precursors like NIPS, Spark, so forth. But what's interesting about RISC-V is it's not associated with a company. It is an entity on it to itself, and it has less entanglement from, say, an open power perspective with IBM. So that's the exciting part, is how do we use these to then drive the ecosystem and make something useful? And so as a result of looking at this specialization, what we'll see is, future HPC systems will be customized. And so we'll have a variety of different things, from things like CPUs, which are general purpose, kind of your Swiss Army knife. They can do everything, to GPUs being used for a variety of different computations. FPGAs give you a malleable hardware infrastructure that are good for different type of interesting things. A huge upsurge in machine learning accelerators or AI accelerators. And there's a bunch of different people, startups doing this, from GraphCore to Samba Nova, Esperanto, Cerebras, those types of things, all creating specialized, all the way down to specialized ASICs, and running a bunch of different kind of things. So we have flexibility on one side to efficiency on the other, and then they want to run a bunch of different applications. So that's kind of the exciting part of where we're going. And so what we're saying is, hey, tomorrow or in the near future, let's make HPC open completely. And so with RISC-V, I break this barrier at the CPU, GPU, and ASIC level of being able to specify and use a compatibility layer, which is the ISA, to then drive all of these pieces and create a new ecosystem that can be completely open. Now, this is open from a specification perspective, not necessarily an implementation perspective. So you can still have implementation specific or proprietary components in there, but at least from a research and development, we can leverage open source for some of these components. And RISC-V gives me a language to unify, to focus, and to build a new microelectronics industry. And in particular, we're excited to do that in Europe, right? So we can leverage this ecosystem to then drive the digital autonomy, digital sovereignty questions from an HPC perspective, all the way down to IoT. So that's really what we're trying to drive here in terms of thinking about this in its overall perspective and going from there. So this probably is preaching to the choir, but it's useful to say, okay, well, why open source hardware? Right. So obviously we want to leverage compatibility in software. There's a bunch of security components and concerns, right? If I can look into the code, I can create something that's fully auditable and make sure that there's no backdoors from a safety perspective, no black boxes. Because I have this component, I started off with the size, weight, power, those types of things as the code design metric, right, for customization and enabling software hardware co-design. I can get to state-of-the-art performance with state-of-the-art implementations using the latest TSMC, Intel, Samsung, whoever foundries to drive this. I can have less vendor lock-in, so I can go to multiple different parties to provide this. It's not just x86 or Power or ARM or whatever. And again, as I was driving earlier, this notion of how do I create freedom of access for implementation of these designs. There's still a lot of work to go from concept, RTL implementation, the code that defines the hardware, to actually creating a physical chip. But I get this ability to have the top levels at least be a little bit more free. And then fundamentally, with all open source, this notion of open collaboration, faster time to market, leveraging the community existing components is great. And so that's really kind of where we're looking at this, especially from a research and development perspective, helping us. We can collaborate like we collaborate on Linux and other components. And obviously, the challenge there is to make sure you prevent fragmentation, you create an ecosystem that's sustainable, both from a financial and an intellectual capital perspective. So I've said a lot about RISC-V. What is it? Let's kind of define that from a high level, and then we'll go down. So RISC-V is defining another instruction set architecture, or ISA. And so it's useful to say what an ISA is, right? This is basically this abstract model of what a computer can do. It's a set of instructions and other things. And this is the contract between the programmer writing the software and the hardware. And obviously the compiler does the interpretation from high level languages down to the actual assembly code and so forth. And so really what I'm trying to make sure, and I'm not going to go through all these, is but you already play with ISAs every day, right? If you're running something on an x86 from Intel or AMD, if you're running, right, those are all specific ISAs that allow you to have code capabilities and compatibility there. ARM, right? Fugaku, in terms of the top one in the top 500, has an ARM ISA. So we're already familiar with these things, and they're everywhere. And so RISC-V is yet another one. But the difference here is I, as an individual or anyone, can go through and say, hey, this instruction is missing from this instruction set architecture. I would like to implement it. And now I can. And I can go even further and say, hey, to the community, this is a great idea. Here is my idea. Here's how it impacts the world. This will make your processor, accelerator, whatever better. Let's put this into the standard. And so that's part of the excitement there, is that I can actually do customizations. I can keep them to myself, or I can share them with the community. Whereas if I look at these other ones, that's not possible. So as we drive deeper, right, as I mentioned, in about 2010, Berkeley started to do the initial development and proposal for it. They later spun this out into the RISC-V Foundation in 2015. It's been adopted by many companies. They've shipped, as of 2019, over 1 billion CPUs. They moved the foundation from the US to Switzerland to be more neutral. And so using the Swiss neutrality as a overarching process, putting it into the public domain that way. And then as recently as 2021, last year, there's been documented over 2 billion cores shipped. So we're getting a lot of traction and momentum within the RISC-V community, albeit from the embedded side. So these cores are embedded in your soldering iron, in your smartwatch, in auxiliary processors for power management, those types of things. So you're not necessarily going to see them. And so what we're saying here from a Barcelona Supercomputing Center side is, hey, this architecture, this ISA, we can also use for supercomputers. And we did this about 10 years ago when we started the Mont Blanc project. This was a scenario where we took Samsung cell phone processors and compose those into a supercomputer. And a decade later, Fugaku came along from Fujitsu, and we now have that as a very exciting system in general. So we're seeing the same type of trends here. And in this case, the ISA is open, so we can actually do software hardware co-design, where that wasn't the case with ARM, x86, and whatnot. So that's the exciting part. So when we take a look at this, right, this whole open ecosystem, right, we want to put it in this new domain of looking at, okay, well, we have things like GROMACS, we have the different libraries, we have the schedulers and components, tool chains, GCC, LLVM, various versions of Linux, right? All of these things in the open source domain can be recompiled and retargeted, specialized for RISC-V. And what I'm showing here is on GitHub, there is a slightly deprecated list of what's available and can run today on RISC-V. And so the exciting part is to keep moving that in that direction. And one of the things that we're working on as part of the special interest group on high performance computing, which I'll get into a little bit later, is a CI automation framework using Jenkins to be able to automatically test, can I compile libraries, software, what have you, either cross-compile or natively for RISC-V. So that's kind of part of the big nut we have to crack, is running software and compiling software and making sure it works for RISC-V. And the other part is developing the hardware, and we're trying to do both. Now, this is not something that we're doing alone, and there's an entire ecosystem around RISC-V, right? So there's a bunch of different application spaces, all the stack I just went through. RISC-V is really defining this architectural test and the formal models and the instruction set. They're the organization to try and keep everything well-defined and have the procedure and process, where the implementations are done by a variety of different companies. They're out there, and many that today. And then there's whole aspect of all the tool set, training, CI, CD. So this whole thing, that ecosystem, is what is currently being built today. And so the exciting part is we're getting really good traction. So there's over 2,000 RISC-V members from about 70 different countries. And so again, we're looking at how do we replace existing systems and drive innovation and technology. They're growing at a very rapid rate. And it's what you'd expect from some of the open source components. There are large manufacturers on one side and big companies coming behind RISC-V, as well as a significant number of individuals, as I'm showing here, over 1,900 individual members. And it's interesting, right? If you were to do a comparison, RISC-V has a number of chips, right? There's a bunch of SoC IPs, all these things that can be mapped to silicon or to FPGAs, and that number is growing rapidly. On the system side, right, whether it's I/O or system components, there's not that many. Now, if I do the flip side of this and look at Open Power has a few cores, but they have a lot of system integration components. And so it's just interesting to see the differences between the two systems, but it's something to keep in mind. So, a lot of different things going on with high growth, and we hope to see that continue. And for us particularly, we want to get more folks in HPC excited and using the system and driving to make sure that the ISA and the ecosystem support high performance computing. That's the big thing. So when we look at this again from RISC-V, 40% of these application specific circuits or ASICs will be designed by these OEMs, right? And so that's an increase in the number of people building processors or application specific ICs for this. And so that's an exciting opportunity to push RISC-V in that space and drives growth overall. The interesting thing about the models is pretty straightforward. There's a bunch of things on the impact side. So it's free and open model, right? We want to have this ability to, or there is the ability for everyone to implement and suggest new things. And then we get adoption from a variety of different folks, from HPC cloud services all the way down to IoT. And we're using fabless semiconductors to really drive this. So really, whether it is at the IoT space where it's big now, embedded, or in the cloud space or in HPC, we see huge opportunities to use RISC-V and help you, us, whoever, to actually build systems. And that's the exciting part. And so we have these massive numbers, right? IoT and embedded is incredible in terms of the size. And you'll see in terms of the growth over the next 3 to 5 years across the different connected spaces, there's going to be 50 billion connected devices. Now, from an HPC perspective, that's great because those devices generate data that then will be used in simulation or other types of high performance applications. But we're now seeing this world where there's lots of connected devices, and that's either creating more data or other things. But again, it's not just that space. HPC now can benefit as well. On the overall market side, these numbers continue to be revised. So 2 years ago, they were predicting about 50 billion RISC-V cores in 2025. That's been increased to 80 billion. And so that's the exciting part of there's just more and more opportunity, and it's a high growth area. And in this context, we still want to say, okay, well, HPC can benefit as well. And so that's where leveraging the open source and the industrial growth gives opportunities for everyone in that space. Now, in the interesting aspect, right, again, 4,000 individual members working on a variety of different projects. The foundation is the infrastructure around which we can build all these pieces, of which I'll talk about the special interest group for high performance computing, but they have people interested in memory systems, in programming languages, memory models, all these things to really drive an ecosystem and provide a better environment to run applications. And when we look at the platforms, it's IoT, it's data center, HPC, all those things, automotive. There's all these different opportunities to contribute. And I want to make sure from the high performance computing side, we're also involved in those conversations, and we make sure that the specification covers that. So those are the fun parts of that. So diving specifically into high performance computing, we created a special interest group, and the whole focus is to make sure that HPC specific requirements are included in RISC-V. And this is everything from virtual address memory sizes to other components and software, and I'll get into some of the details that we're doing there. And so it's always part of this process to push RISC-V outside of its current environment, like we did with ARM. So from a vision perspective, really, we're trying to provide technical and strategic imperatives to guide the RISC-V ecosystem, right? And get us to this open HPC ecosystem where now we have everything from the hardware to the software has the capability to be open. And we want to enable the software and the hardware in that space, right? And for me, high performance computing not only is the traditional high performance computing components like ROMAX and other things, CFD, whatever, it also includes the AI, machine learning, and deep learning components because a lot of the base kernels are the same. I'm using BLAS in AI, I'm using BLAS in HPC. Doesn't matter. So if we can use both of those in terms of thinking about holistically what my base level algorithms are, then we can see how there's applications across the board. And really, we're trying to make sure that we capture that. So what that means is to usher in this open era, it's talking about CPUs, accelerators, hardware, verification, software ecosystem, alignment, all these components that really drive opportunities both for our industrial partners and our academic research partners to enable this ecosystem and really support this kind of independent technology and make sure that there's a roadmap within HPC that benefits us all. And so that's a conversation I think we should all have. Now, in terms of initiatives, and guiding the community, we talked about a variety of different things. So Intel just came out with its virtual address space extensions up to 57 bits, right? And so again, we want RISC-V to support 57 bits because it doesn't go that high. This 57K is this notion of having separate kernel and user pages from a securities perspective. And so that gives us even more functionality than what the Intel specification is. Moving beyond that, getting to 64 bits is interesting, right? We need 60 bits for an exabyte of DRAM to do an addressing of that. So 64 bits gives us that capability. And then even moving forward beyond that, what about 128-bit address spaces? This is where we could use features for security, for partition global address space computations, really pushing us beyond what we're doing. And when we think about exabytes and exaflops, how do we want to build those systems, moving to zettascale and so forth. We're also talking about, okay, well, what is the HPC software and hardware ecosystem roadmaps? And this is, I think, very apropos to this group in understanding what is required to support HPC computations, the software stacks, and those types of things. And again, then moving lower into making sure that we're in line. So I think EasyBuild is a great venue to have those conversations. And then there's the normal stuff like accelerators, ISA extensions. And today I'll talk a little bit about the HPC software stack, because that's where we're starting in terms of automation, and that makes it an easy process. So, one of the easier things to do is which big rocks can I move first? And so when I think about that, if I can target the libraries that support a bunch of different applications, that's where we're starting, and that makes it a little bit more tractable in terms of getting stuff done. So when I think about this, one of the people I work with, the coach, the vice chair of the SIG-HPC is John Liddell from Tactical Computing in the US. He's doing a bunch of different components, but really this HPC software testbed was one of the first things that we could address to then say, okay, well, what runs on RISC-V? And that can either be cross-compiled or native compiled, depending on your platforms. And I'll get into some of those platforms later. We basically broke up the category of software into 4 different categories, and it made it pretty straightforward to think about. So I talked about the libraries. So, things like BLAS, FFTW, MUMPS, those types of things. These give me a baseline. And so can I just compile those? We get into benchmarks, which are a little bit more intense, but they're generally not as complex as actual applications. And obviously we have tools. So all of these things we want to be able to run on RISC-V, and I can go to show later what we're running on some of our clusters. But fundamentally, we're starting in this space to get us to the next level and say, not only that RISC-V runs whatever, it also runs HPC workloads. And so you can actually deploy full stacks on that. That's what we want to get to. So in the software test bed, and this is obviously working within the confines of RISC-V International, we've created this Jenkins pipeline, and it's pretty straightforward, right? We have a couple of them, one for GCC and one for LLVM. And these pipelines are just doing 2 things. They're testing the compiler itself, and they're just testing what the compiler can do. So over time, we can do different revs, versions of the compiler as well as different versions of the library. We want to come up with, a dashboard that says all of the stuff runs on this version and so forth, and track that. But you start with a request, pull request. It does a build. It can do GCC or LLVM. It can do a deploy of various parallel builds of the application. And then that, excuse me, the results are pushed back. And if it successfully compiles, we can check that off as something that compiles. But this is something that was missing, right? Just knowing what can work in the RISC-V ecosystem is what we're trying to discover. And then once we understand if there's compilation errors, whether it's a compiler problem or an application problem, then you can go back and create bugs or whatever and file those issues with the corresponding software ecosystem components. So that's the fun part. In there, it's a kind of traditional flow. We have the different projects and versions of LLVM or GCC, and we push those out, and we understand kind of duration and if there are failures in this process. So it's all pretty straightforward, and you can go to the website to check it out now if you'd like to. It's pretty straightforward. We want to put the whole CI/CD infrastructure in open source so other people can use it and deploy. And the nice thing is that since it's a public infrastructure front end, you can actually map it to multiple hardware backends. And so one of the next things we want to do is run not only stuff in John's data center in Austin, but also in our space in Barcelona. And so now we have a kind of universal space where we can do this testing and get the results from. So, goes through the normal things that you would expect in terms of the process and the build, and the results are public. And as I mentioned, this test harness is public. So you can actually go and see the repos and provide some interesting components there. So it's, again, trying to use industry standard components to really drive this whole ecosystem forward. And that's kind of the fun part. And then getting an infrastructure that's global. And so working with RISC-V, building up RISC-V labs, all those things that then can do this CI deployment and drive at least understanding of where we are. And then once you've measured, you have metrics and you can actually make improvement. So exciting to you, kind of Jenkins and those normal components. So in this concept, right, what we're really doing is getting this ability to build this open ecosystem with RISC-V, right? We can do the customization of the hardware and fulfill the hardware software co-design that HPC domains require. We can, tackle these grand challenges and have a global ecosystem to drive that, and basically continue to have HPC on the leading edge with leading edge components that have more inputs from various people, whether it's research or industry. And so all of this is combined into this open source ecosystem on the ISA side that now does a very good complement for the software stacks that everyone knows and loves. And so now we have this combined component of hardware and software that then give us a full ecosystem. And what we're excited about from a research perspective is we have a language, tools to accelerate those conversations and the innovation, and obviously build from the RISC-V community. So all those things come together in a very exciting space. Now, all that's good, right, John? You've told me all this stuff, blah, blah, blah. I don't care. I don't have a RISC-V, right? I think that's what I would hear first. This is the first time I've heard of RISC-V. What do I do? Well, from our perspective, it's a little bit more involved than that, in the sense that, yes, if you've never heard about RISC-V and combining that with HPC, you're not alone. However, there's things that you can do as well. So what I've pulled out here is a bunch of different board vendors, right? So PolarFire, Beagle's kind of going to be replaced. Unmatched is coming from Sci-Fi, and Allwinner is a vector extension board. We're running Fedora or Ubuntu on them. They have a certain number of cores with memory. Probably Unmatched is going to be closer to what you want, because 2 gigs is not enough to do a compile of GCC or LLVM. But we also have a bunch of different things running from a software side. So we're running Linux. We're using Slurm on RISC-V to control and do the resource management. We have a bunch of compilers running on them, from LLVM and so forth, Go, Python. We have a bunch of both HPC tools, like Xraya is a visualization tool. Pappy gives you your performance counters. There's Perf Singularity from a container perspective, and then also a bunch of libraries that support the applications that run on top of that, like, say, GrowMax, which just released a patch, I think, in November. So all of these things give me kind of the initial ingredients to start running real code on real hardware. And so this is one place to start. but that's not it, right? That's not all. There is more, right? And if you don't have access to hardware, there's access to software, and I'll get into how you can play with that. But before I move into more of the getting started piece, you also can get involved, right? So the SIG-HPC is specifically for creating issues and making sure RISC-V is addressing the high performance computing environment ecosystem. And folks, we have a place online, and obviously if you'd like to subscribe, you can subscribe. Our meetings are every third Thursday of the month at 4 o'clock in the afternoon. The next one is February 17th. So if you're interested, please subscribe and reach out. And obviously this stuff will be available, links and so forth on the slides. Now, I've showed you some of those pieces, and I want to do a couple of things. One, I want to get give you some understanding of how we're getting started, and then give you the tools to get started as well. So I've showed you some of the boards, but I want to dive a little bit deeper in terms of the BSC, right? So what we've been doing is we're building a bunch of cores and accelerators in these different projects. So there's a European processor initiative, DRAC is a processor project, and we have all of these things that are taking us from research to industry and production to build up this ecosystem. So the MEEP project is a FPGA emulation platform, large scale. We have an out-of-order processor project called eProcessor, and these are, either Spanish or EU projects that are funded by Horizon Europe or the Euro HPC joint undertaking. There's a European pilot, which is building two different types of RISC-V accelerators. One is a vector accelerator. The other is a stencil and machine learning accelerator. There's the second phase of EPI, the European Processor Initiative. All of these things are combined to create IP infrastructure today. And so it's a new kind of growth area in terms of resources and people excited about RISC-V in research, and that will translate into later products that are built by companies. And obviously there's many more projects and people coming on board, but this is the start. So you're seeing the beginning of this growth phase of open source hardware in high performance computing specifically, and driving there. So it's not something that I'm just talking about of, oh, hey, use these embedded things to do this stuff. It is, we have projects, the Euro HPC joint undertaking, Key Digital Technologies joint undertaking are all producing calls that are driving efforts and resources in the open source hardware space. And ideally RISC-V is the candidate to be used there. Now, the final piece of this that I want to say is, okay, I've showed you some boards you can get, right? And here's a link to the boards that are available that you can order today. But if you just have a Linux box, you can get QEMU and do a software emulation of that. And there's a couple of different ways you can start. If you're an Ubuntu fan, they have a wiki getting started guide. If you prefer Fedora, you've done that. I know Kenneth has actually done this as well for EasyBuild. And so there's 3 different resources here to give you hopefully a startup guide to get you to a place where you can just play, right? So now you have a RISC-V ecosystem running in software on your Linux box to then say, okay, can I compile this? Can I run this? My software does this. Now, let me provide some caveats. Nothing is a free lunch from that perspective. In the traditional C++ world, life is great. If you're running Fortran code, RISC-V is not for you. We're still a little bit early on the Fortran side from the standpoint the Fortran compiler is still under development and immature. So folks from NVIDIA are working on the front end through Pacific Northwest Labs. And as soon as that LLVM front end becomes available, that unlocks a lot of things, because once the front end is there, then all the other LLVM components, whether it's vectorization code or what have you, can then be applied. And we're doing a bunch of stuff with LLVM. The GCC side is still not as mature. I think it's further along than LLVM is, but it doesn't get you to run and compile Fortran codes as of today. So depending on your ecosystem and your requirements, if you're doing C++ stuff, the RISC-V components can be worked on today. If you're doing Fortran, that's a challenge. There is Python support, there is Java support. Those are limited and so you're not going to get everything that you'd say get in the x86 world. So I just want to give you some buyer beware in the context of you're on the bleeding edge, and so things need to be developed. If you're excited about these ecosystems, obviously you can contribute as well, but those are the different components there. So getting started guides are here, and you can play with it. They're relatively straightforward. You can buy a board, and if you buy one of these boards, they have pre-built versions of Fedora and Ubuntu that you can download depending on the manufacturer and walk through those processes and then come up with that. And as I mentioned, we're creating clusters that we can make available so people can have a sandbox to play on real hardware as well, depending on what you do. And the 16 gigabyte boards tend to be better because you can compile LLVM and compile the components all there. There's enough memory footprint to do that. So hopefully today you've pulled out and said, hey, there's some interesting things on the horizon. I've touched on the research side. I've given you hopefully some motivation for driving what's going on in RISC-V today, and giving you some tools either to run it on your Linux box, buy the hardware. You potentially could request the hardware from, or a dev board from RISC-V International as well, and then gives you the tools to start looking at what the future may hold, and we're building towards that. With that, I'm going to pause and answer any questions you guys may have.
Thank you, John. Okay, had his hand up first, so we'll go there.
Yeah. Going back to the DEC Alpha system, has there been an interest in native 128-bit floating point operations?
That's a great question. So in the EPI project, there is CEA, the French Atomic Agency, which is building what they're calling a VRP processor, variable precision processor. They support 128 and 256-bit floating point operations. So there is some interest. They're very usually specialized, but there is a processor that was built, and that processor was fabricated. So EPI was the VRP, it was a vector processor, and the stencil and machine learning processor all in a single chip. So they put 3 or 4 different projects together, and so that exists today.
Yeah, nice. I always dislike this reduced double precision. I like precision.
Well, I mean, so this is the big challenge, and this is the thing that differentiates machine learning, AI, and deep learning, as you know, right? They're going 8-bit, 16-bit or smaller, and HPC is always 64-bit or larger. And so this is one of those things of understanding where you can go. And it's funny because I'll have conversations with AI vendors who are super excited to say, hey, we want you to be a customer of our thing. And then they say, well, we only do 32-bit single precision floating point. And I have to go back and say, okay, well, I don't think we have any applications that do that. Are there ones we can find? And so, or you do soft float or something like that to get there. So you lose out on the application specific nature of using the 32-bit stuff, but there are workarounds like soft float that can get you there. So, and then there are certain agencies that are interested in higher precision, and that's fine too. But traditionally we do 64-bit.
Yeah. Thanks.
Sure.
I have 2 different questions, unless somebody comes up with another one in between. So the first one I have is, can you make any predictions on when we'll see the first supercomputer, let's say a top 500 supercomputer that is running or that is using RISC-V CPUs? Do you see that in the coming decade, or is that too ambitious?
I mean, so there's 2 pieces to this, and let me kind of separate those. All predictions past 5 years are probably useless. So let me put that disclaimer out there. However, you asked me a question, so I'm going to make a prediction. What I see that we can do first is focus on accelerators, and accelerators give us a smaller software surface area. And so we'll see RISC-V accelerators in that space, and within the decade, between now and 2030, there'll be RISC-V accelerators for HPC that will be built and used in HPC. And that's really what we're driving for. So all the research that we're doing is focused on that as a first tractable space. The next thing that's harder is the general purpose processor. I need to run all codes, and I need to have capabilities, whether it's functional or non-functional, that meet what the competitors do, whether that's a Xeon Core, or AMD EPYC, Power, blah, blah, pick your favorite one, right? ARM, right? So there's a lot of maturity that has to happen within the RISC-V ecosystem to provide that. That would be a challenge to do it within the decade. It is possible. Now, if I look at what we did with Mont Blanc, that proposal process started like 2008, 2009, and we moved forward. And I think it was maybe the last supercomputing I was at was in 2019. And I remember there was some BOF which was saying, okay, bird is a feather. Is ARM going to be a supercomputing, in the top 500? 2019, people were like, no. Like majority of the people said no. For the last 18 months, we've got Fugaku. So it's a very interesting thing to see how things can change rapidly. And obviously Fujitsu and the co-design that's happened at RIKEN, that's awesome. And we have the same opportunity, but it can happen in a more global context. So I'm hopeful, right? I'm optimistically hopeful that we can accelerate that process. The geopolitics and all these other things kind of complicate things. So that's why I can't have a high certainty, but ideally we can do what we did in terms of demonstrating ARM in HPC. We're doing that in RISC-V, and that will accelerate it to be realized. And the question is, who's going to do that? And so that's the challenge. And what we're seeing with the European Chip Act and some other things are driving to this opportunity that exists. The question is, who's going to pay for it? And so if Europe truly wants autonomy, they need to move beyond that, because what I see now is in the embedded space, you have Infineon, NXP, ST Micro, like there's a whole bunch of folks within Europe that can use RISC-V and go from there. And it stops there, right? We don't even have a cell phone processor manufacturer or provider developer here, right? So we need to move that up. And what we're doing with the SIG is saying, from the specification purposes, we want RISC-V to be a player in HPC. And so, can we do it in 8 years? It's possible. But it's a large investment, and we would need global help for that. So accelerators definitely in HPC, processors, lower confidence, but I would hope so.
And a big part of that is going to be the software stack as well. So that's actually my second question. We had a presentation last year in the EasyBuild community on Bliss, which is the BLAS library, very similar to Open BLAS, but let's say a more modern design. They have a very interesting low-level approach of how they're doing things. And when we mentioned RISC-V, when we were asking for support for RISC-V, the lead developer of Bliss was just unaware. Yeah, he was just unaware that RISC-V was a thing. So he didn't actually know there was an extra ISA like ARM and Power and things like this. And that was a big surprise for me, because he's working with this low-level assembly stuff all the time, and he didn't know that RISC-V even existed. So it seems like you're doing this software test bed and reaching out to projects to let them know that it's not working on RISC-V. Are you also already doing or considering going a step beyond that and maybe engaging with projects and say, look, it's not working on RISC-V, but let us help you and let us show you how you can get access to a board or an emulated system you can play around on, and if you're ask us if you need help or things like this, or maybe training sessions on how to get started on RISC-V. Is that something you're considering as well? Because it seems like that could be a big help, a catalyst even.
Yeah, you are touching on so many different things. So let me try to address all the different points. One is brand awareness, right? Just awareness that RISC-V exists. So last year there was a first involvement in ISC. And so we had a session on RISC-V, and RISC-V International had a virtual booth there to try and get awareness, because in the HPC community, no one knows, right? And so we're trying to address that. That's kind of number one. Being involved at ISC, being involved at SC are getting us there. these type of conversations that I'm having today, really driving that or doing that. On the research side, having research projects that are using RISC-V, having calls in the HPC, Euro HPC, whatever context that request open source hardware and RISC-V specifically, as an example of open source hardware, are going to provide awareness. In my projects that I have going on right now, whether it's MEEP or eProcessor or these other things, we're actually working with Bliss. And so we're taking these libraries and doing that and saying, okay, how do we optimize for RISC-V for an accelerator? What does that mean? Does that change that things? How do we impact OpenMP? What do we think that is specific for this? How do we drive not only it for RISC-V, but broader accelerators in general? So there's broad appeal. I want to put multiple accelerators behind a host. What does that mean? And so that aspect is going on. Within the European pilot project, we're working with KTH specifically on GROMACS to say, how do I optimize GROMACS for a vector accelerator that's RISC-V or this other accelerator? How do you think about RISC-V in these contexts? So we're putting together the software stack and the hardware stack together, right? And all those things are coming. It's a big, the software ecosystem is huge. So the question is, how do we get the biggest bang for the buck? Things like GROMACS, things like Bliss or BLAST, FFTW, the baseline components where we're looking are trying to get that support in place, so then the upper level applications might not care about this because it's already built into the library. So all of those things are moving together. Brand awareness or RISC-V awareness in HPC, tackling some of the libraries, and Bliss is a good example. GROMACS at the application level, because there's so many different applications that use GROMACS kind of as a library, and doing that in the research areas, building up stuff for deep learning and machine learning, same type of libraries like 1DNN or things like that. So all of these things are coming together, making sure TensorFlow runs on RISC-V, Apache Spark, these other type of high performance data analytic frameworks, and those have limitations because of language like Java support. So there's a bunch of different big pieces that we can move, and obviously we're hyper aware of the HPC specific things. And so that testbed is one way to get us there closer and automate it, because we all have day jobs. And so we need to throw in the automation. I mean, I'm sure you guys are big on automation in general. I tell everyone, automate yourself out of a job so you can do other things. So we're trying to do that in infrastructure and CI/CD side. The other part of that is in China, they have a really good RISC-V ecosystem as a lab. So I'm trying to get RISC-V labs specifically for HPC, both in Europe, where we have sandboxes where people can play with them, as well as in the US. So John is kind of covering the US, I'm covering Europe, and then we can basically, much like Barcelona Supercomputing Center, about 50% of its cycles are European cycles, right? And so from that perspective, we could do the same type of thing with a RISC-V hardware lab that people could play with. And ideally, I could say, send email to this thing to set yourself up with an account, and then boom, you can play with a RISC-V sandbox, right? And do the same type of reservation process. So that's where I'm trying to get to and get us, get that awareness out there and support. So hopefully, did that answer all your questions there?
Yeah, I think I answered most of them. To your last point, you're trying to set up a physical, let's say, a cluster with RISC-V boards that people could get access to for development purposes and testing.
Yeah.
And do you have a timeline in mind there? Is that like months away, years away? This year.
No, it's this year, right? The question comes, so I have these systems here today, and what they're doing is they're supporting the various research projects that I showed on the other page, right? So we emulate our research platforms in real hardware, and then we can add trap instructions for things that won't execute, like vector instructions on the unmatched board. They don't, obviously there are no vector instructions there. So we trap on those, and then we can do some other emulation ecosystem there from a simulation perspective. So those are places where I currently have things pre-allocated for the projects, and I want to acquire additional systems that then can be used externally. And these projects have multiple partners. So there might be 10, 12, 20 partners in the project. They all have access. So they're not just BSc people. So the infrastructure is there. It just is, there's not enough to openly let the community in Europe use, and I want to organize the lab and have support not only internally at BSC from an ops perspective. So I need sysadmins and those guys there. And then I need more support from RISC-V, which I just have to ask for. It's like, okay, BSC is committed to creating a European RISC-V lab. We want to do X, Y, and Z. Give me boards, provide this publication, publicity. Let's create the user account management stuff, right? And just put all that together. So those are the steps I need to go through. But I'm just showing this because we have boards and there are external users for them, but they're within the project. And I like to make it be open to everyone in the HPC community.
How are the price points for these boards? Like the unmatched, is it like a couple €100 or?
Unmatched is about $500–600. Okay. The all winners are about $100, I believe. Beagle is being redone by Starfire, and the PolarFires are FPGA plus processors, and so those I think are around 600. So, what we're trying to do in general is look at something that's useful from an HPC perspective, which is basically this unmatched board, right? Those are the best things because of memory size, not because of processors or anything else. The challenge that we have as well is with the global supply chain, lead times on these boards have been pretty high. And so what I can try to do is working with RISC-V International is get to the front of the line to then provide this resource to enable them in the ecosystem. And the people who build the boards obviously want that too, because the more people that use them, that is good for them in the future in terms of their IP or whatever they're selling. So the all-winner board that has vector supports coming out of China, that's kind of, I think there's going to be a Raspberry Pi kind of 50, 100 price points, and then these higher ones. And ideally, we can make all of those available.
There's actually a Raspberry Pi RISC-V clone already there. No, I
Yes.
forgot the name, but it's like another fruit.
Yeah.
I forgot the exact name.
The problem with a lot of these smaller boards is you don't have the memory capacity to do useful things, especially in the HPC side. So that's the thing.
Have you considered setting up essentially a Slurm cluster where RISC-V is just emulated with QEMU, or would that be too limiting? I mean, it will be slowish, but if the hardware is fast enough, maybe that doesn't matter too much.
So right now, what I have in this cluster, the Fedora Beagle board is my Slurm master, and it actually controls a bunch of the unmatched boards for resource management purposes. So I'm doing it natively. We found that QEMU is a little bit slow for real-time application development if you're trying to do something that's not research focused. So my goal would be to provide hardware where you actually can play with it and then do the resource partitioning and all those things. But we want to run a complete HPC stack. So, that's where it becomes interesting. And, the libraries and compilers I'm showing are really drive and focused on supporting that.
Unless there's any, it's Mango Pi actually, the Raspberry Pi clone. Yeah, that's the one. That was pretty recent. Yeah. I have one more question maybe to wrap up with. Quite recently in the EasyBuild community, we've had a bit more focus on ARM. Let's say probably fueled by things like Fugaku, and we see things moving there as well. And we expect more ARM-based supercomputers to come up, and we want to be ready for that. We've also looked at some bioinformatics tools where we were trying to build them on ARM. That was not really working, and we reached out to those developers, and they basically said, "It's ARM. I don't care. First of all, I don't have the resources or the time to help you out, and second of all, I don't really care because it's ARM. Nobody's using it." So it seems like even for ARM, there's still quite a bit of work to be done, but that's probably going to happen. I mean, they can ignore ARM today, they probably can't ignore ARM next year, let's say. Do you think that some of that work will actually pave the way for RISC-V once people realize there's more out there than Intel CPUs? Once they're also supporting ARM, I guess the jump to supporting yet another ISA will be a lot smaller, I guess. Do you think that's true, or is that optimistic?
So there's a couple different paths there. One that I'm optimistic about is it works on x86. They get, pestered and bothered to make it work on ARM. They say, no, 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 I can't do that, but here's an open source version that you can make work on ARM. Once you have an open source version of that code, then we can port it to RISC-V if porting is required. And so I think that's an interesting path as we go through. What I've seen companies do is they support mainline x86. They may open up support for Power, ARM, RISC-V, whatever, and it's up to you to do the last 5 or 10% to customize it for that application and do whatever is required. So that's one path forward. The other path forward is we're using research to drive specialized hardware and optimizations like for GROMACS, for Bliss, and those types of things. That's the other piece that I'm hoping. But again, you're starting with code that's already open source, so it's a much easier process. If there are particular closed source applications, we need to get a groundswell of hardware and you need to demonstrate, right? I mean, one of the things is if I can show RISC-V running an application that's a competitor, an open source competitor to a closed source application, that's an interesting space. But I think what I see right now is exactly what you're seeing, right? ARM is still kind of the bastard child, right? They're not really getting a lot of attention because everyone's running x86 or they're running GPU code or what have you. And GPU code makes some stuff easier, some stuff hard. With the entrant of Grace and NVIDIA in the space of ARM, that actually gives you a more credible solution, because up until then, it seemed that ARM servers had peaked. And so now the question is, what will happen with Grace and how will that do? So I think ARM will come up on that level in that space. And in the accelerator components, it's a little bit easier lift, but as RISC-V gains momentum, I think, we'll see that what happens. And my hope is, if at least in Europe, we're seeing a lot of research support for RISC-V, which will translate into software support. And so we'll have calls for RISC-V hardware and RISC-V software ecosystems to be developed. And so that's going to help a lot.
Right. The Bliss thing, you say you're working together with Bliss. Did that happen in the last year?
This is a recent, this is within the last year. So we're taking the Bliss code and optimizing it. I don't know if there's much conversations between the Bliss maintainers, but we're just taking that open source and driving that. And I can definitely connect people if that needs to happen as well.
Mm-hmm. Yeah, I would hope that the Bliss maintainers, or let's say the lead developer, is now more aware of RISC-V.
I would hope so. I mean, but you need to create a branch and start being aware.
It's extra work for them. But yeah, they actively do research, so I hope they see the value of RISC-V as well. For them.
Yeah, and the great thing is you can now. I mean, the thing that's unique is I now, instead of have to think about what I'm going to fit into AVX 512 or my MMA, my matrix multiply unit, or those types of things, I can say, hey, for this thing, if I had this hardware widget, it could do some amazing things. And that's where Bliss could, move beyond what's available in hardware today.
All right. Yep. I don't see any other questions, so I think we're ready to wrap up here. Thanks a lot, John. This was a very nice talk to end the EasyBuild user meeting with this year. I'm very much looking forward to what's going to happen with RISC-V in the coming years. So thanks a lot.
Me too, and I'm excited that EasyBuild is supporting RISC-V. So thank you very much. And as I mentioned, if there's how you want to participate, contribute, there's space in RISC-V International and the HPC SIG. Please join, and I'm hoping to get suggestions and all those great things. So thank you for your time, everyone.
Right. Thanks.
Take care.